Hi! Today we're going to learn about the second derivative test in calculus. Let's say we have to find all of the local minimums for f of x is equal to x cubed over 3 plus x squared over 2 minus 20x. So we know that to calculate minimums and maximums, we have to find when the first derivative is equal to 0. So let's do that. So let's first take the first derivative. So f prime of x is equal to x squared, using the power rule, plus x minus 20. So now we have to set this equal to 0 and solve for what x would be. So we know that this is a trinomial. It's a quadratic trinomial, so it's a product of two binomials. So one's x plus something, and the other one has to be x minus something, because this is a plus and this is a minus. Now because this is a plus, that means that whatever value we put here has to be larger than the value that we put here. And when you add them together, they have to be equal to 1. So the two values that when you add them together equal 1, and when you multiply become negative 20, would have to be 5 and negative 4. So it would be plus 5 and minus 4 is equal to 0. So that means that x is equal to negative 5 or positive 4. So now what would we do? Well, in the first derivative test, we would make a sine line and then put these on the sine line and calculate the sines and see where the graph's first derivative changes from negative to positive. However, in this video, we're going to do the second derivative test. So let's take a quick break from here and go to something else. So let's say that we had a chart. Let's say this was direction, up, down, and this was concavity, up, down, and let's fill out this chart. So take a moment to fill it out first by yourself. So if we have concave up and it's increasing, that means that it's like this. If we had concave down and it's increasing still, then it's like this. If we had concave up but it's down, then it goes like this. And if we had concave down and it's down, that means it goes like this. Or actually, sorry, these two flip. Whoops, sorry. So if it's concave up and it's going down, it goes like this. And if it's concave down and it's decreasing, it goes like this. So, what does this tell us? Well, this tells us that if we're trying to find whether these are minimums and maximums, we can look at the concavity. If it's concave up, so now let's take whatever we know, and let's just do it with just concavity instead of direction. So if we had something that was concave up, then it would look like this. If we had something that was concave down, oops, I sort of need to erase this. Can you see this? Let me check. So, let's say this was concave up. So this would have to be concave up, because on this side, if we split this in the middle, on this side it would be concave up and increasing. So it would be this one. On this side, it would be concave up and decreasing. Like there. So now I hope you've gotten a good picture of this. Now let's do concave down. I'm going to just redraw it here smaller. In concave down, you would have it like this. So this would be concave down and decreasing, and this would be concave down and increasing. So let's look at these two for a moment and see a pattern between them and what we're looking for in this problem. So take a moment to find the pattern between them. Alright, so what we're looking for correlates with the concavity. So I hope you notice that when it's concave up, we have a minimum, and when it's concave down, we have a maximum. So this is always true. So we can generalize the second derivative test as saying, so let's write this on the side. So if you have a point C such that the first derivative is equal to 0 at point C, so let me write this. If you have a point C such that f prime of C is equal to 0, then if f double prime of C is greater than a 0, then it is a minimum. So I'm just going to use min for minimum. If f double prime of C is less than 0, then it is a maximum. So we can see these from the two examples that we have. So if f of double prime of C is greater than 0, then that means that it's concave up. And if it's concave up, we saw from that graph that was right here before I erased it, that we have a minimum. If f double prime of C is less than 0, that means it's negative and it's concave down. And as we saw from the graph that was over here before I erased it, when it's concave down, you have a maximum. And then the last thing is, if f double prime of C is equal to 0, then the test fails. So if f double prime of C is equal to 0, then the test fails, and then you have to do a sign line to figure out whether it's a minimum or maximum. So we can generalize this as the second derivative test. So basically, you take the second derivative of the function, then you plug in your points where the first derivative is equal to 0, so your x values where the first derivative is equal to 0. You plug those into the second derivative, and if it comes out to be greater than 0, then it's a minimum. If it comes out to be less than 0, then it's a maximum. If it comes out to be equal to 0, then you have to take these 2 points again and make a sign line. And then that's how you calculate them, make minimum and maximum. which we did in other videos before this. So now let's calculate the second derivative. So f double prime of x would be, now let's use this top function here because we don't want to use the product rule, or the product rule. So we get 2x plus 1 is f double prime of x. So now let's plug in f double prime of 5. So f double prime of 5 would be equal to, or negative 5, sorry. F double prime of negative 5 would be equal to, when you get negative 5 times 2 is negative 10, plus 1 is negative 9, and f double prime of 4 is equal to 4 times 2 is 8, plus 1 is 9. So, this problem asks for all the local minimums for f of x. So now let's figure out which one is a minimum. Well, according to the second derivative test, the one that is positive or greater than 0, the one that has a second derivative positive or greater than 0, is the minimum. So in this case, f double prime of 4 is 9, which is positive or greater than 0. So that makes it a local minimum. And because this is a cubic function, and because there are only two values, and because only one of them is greater than 0, there's only one maximum. So, the answer to this problem would have to be at x is equal to 4. So this isn't really a full answer, it's just the answer that we're going to use in this video. But if you had a problem on a test like this, where it said find all of the local minimums, then you could either do the point, so plug in 4 into the original equation, and then you would write that down as one of the local minimums. And in this case, the only local minimums. Today we learned about the second derivative test.